Your computer is pulling off an incredible magic trick. Like right now, as you're listening to this. It's a grand illusion that makes it feel way more powerful than it actually is. So in this explainer, we're going to pull back the curtain and show you exactly how the trick is done. Okay, so let's just jump right into the big question. Have you ever actually thought about this? Your computer might have, say, 8 gigs of RAM, maybe 16, but you can fire up a program that's 20 gigs or even more. How does that work? I mean, logically, it feels like it should just crash, right? But it doesn't. And the secret behind this seemingly impossible feat is a really, really clever bit of engineering. And this is where we get into the real magic. Your operating system, whether it's Windows, Mac OS, whatever, it creates this amazing illusion, a piece of digital sleight of hand that makes your computer feel like it has way more power than its physical parts would suggest. Well, the secret ingredient here is something called virtual memory. And it's important to get this. It's not a physical chip you can buy. It's an abstraction. It's a concept, a clever trick your operating system plays. It basically convinces every single program that it has this massive, private, wide-open stretch of memory all to itself, even though in reality, that's not true at all. So how in the world does the OS create this illusion of all this extra space when it only has limited physical memory to work with? Well, it does it by cleverly managing 2 very different kinds of storage you have inside your computer. And it all boils down to this fundamental trade-off. On one hand, you've got your RAM. It's super fast, like a lightning bolt, but it's also pretty limited in size. And on the other hand, you have your disk storage, your SSD or hard drive. It's way slower, kind of like a tortoise, but it's huge. The genius of the operating system is in how it combines these two, giving you the best of both worlds. So here's the game plan. The OS is smart enough to keep only the parts of a program you're using right this second in that super fast RAM. Everything else, it gets stashed away on the slower but much larger disk. And the most crucial part is the program itself is completely oblivious. It has no idea this juggling act is happening in the background. It just asks for memory, and the OS handles all the complicated choreography. Okay, but what happens when the program suddenly needs a piece of data that's been moved over to that slow disk? Well, this triggers something that sounds like a bad thing, but it's actually a totally normal and critical part of this whole system. It's called a page fault. Now, don't let the name fool you. It sounds bad, right? A fault? But it's not an error, not at all. It's a completely normal, expected event. You can think of it like an alarm bell that goes off, telling the OS, hey, heads up, the program needs this chunk of memory, this page, and it's currently sitting on the disk. You need to go get it. So when that alarm bell rings, the OS just springs into action. First, it pauses the program for a split second. Then it goes and finds that needed page on the disk. It loads it up into RAM, and sometimes it has to kick an old, unused page out of RAM to make room. And then it just resumes the program, which is completely unaware that any of this even happened. All right, so this system is great for running huge programs, but it introduces a whole new problem: speed. Think about it. Every time the program asks for memory, the OS has to do this translation, this lookup, to figure out where that virtual address actually is in physical RAM. If it had to do that millions of times a second, things would get incredibly slow. So we need another trick to speed up the lookup itself. And I'm not exaggerating. Modern programs make millions, sometimes even billions of memory requests every single second. If the OS had to go consult its big master list for every single one of those requests, your computer would slow to an absolute crawl. It'd be like trying to read a book by having to look up every single word in a giant dictionary first. It just wouldn't work. And the solution? Well, it's this brilliant little piece of hardware called the Translation Look-Aside Buffer, or just TLB for short. Honestly, the best way to think about it is as the CPU's own personal cheat sheet. It's a tiny, ridiculously fast piece of memory built right onto the CPU chip, and its only job is to remember the most recent address lookups, so it doesn't have to bother the OS every single time. Now, this is what you want to see: a TLB hit. It's the fast path. The CPU checks its cheat sheet, the TLB, and bam, the address is right there. It gets the physical location instantly. For your computer to feel fast and responsive, this has to happen almost all the time, like over 99% of the time.
But, what happens if the address isn't on that cheat sheet? Well, that's called a TLB miss, and now we have to take the slow path. The CPU has to go all the way out to the main OS page table to find the location. But here's the really clever part. Once it finds that translation, it immediately adds it to the TLB. Why? so that the next time it needs that same address, it'll be a super fast hit.
Okay, so we've got all the building blocks now. We've got virtual memory, we've got page faults, and we have the TLB. So let's put it all together and actually follow one single memory request from the very beginning to the very end.
So let's trace the whole journey. First, the CPU comes up with a virtual address. The very first place it looks is the super fast TLB. If it gets a hit, awesome, we're done, we go straight to memory. But if it's a miss, we have to take the slow path and check the main page table. Then, from there, we have to check if that page is even in RAM. If it's not, we trigger a page fault, which means we have to go all the way to the disk to load the data. It's only after navigating this whole chain that we finally get to access the physical data in RAM.
Yeah, I know, this whole system sounds pretty complicated. There are a lot of steps, but this exact design, it's the bedrock of modern computing. It's what makes everything we do possible. So let's just recap the huge benefits we get from this.
So let's bring it all home. First, the system solves that mystery from the beginning. It lets us run programs that are way, way bigger than our physical RAM. Second, it's incredibly efficient. It only keeps the active, hot parts of a program in that precious fast memory. And finally, that little cheat sheet, the TLB, acts like a turbocharger, making sure that for the vast majority of memory requests, the whole thing feels totally instantaneous.
You know, if all this is still a little fuzzy, maybe the best way to think about it is with a library analogy. Your disk drive, that's the entire library building with all the book stacks. It's huge, but it takes a while to find anything. Your RAM, that's the small stack of books you brought back to your desk that you're actively working with. And the TLB, that's like the sticky notes you've placed on the exact pages you keep flipping back to over and over again. It gives you instant access.
And that's the thing. This great memory illusion is just one of the many hidden systems working tirelessly behind the scenes to make your computer feel simple and seamless. It kind of makes you wonder, what other clever tricks are happening right under your fingertips every single day? Thanks for joining us for this explainer.